Okay, so now our second example is actually going to be a claim that I make to you in general. So here's the claim, and this is going to be part B of our example. So any vector in Rn, that's what we're going to start with. So any vector x, and I'm actually going to write it out in terms of its coordinates here because it's useful to do so. Although I don't want to make any assumptions about this vector x, so I'm going to use unknowns for all of its coordinates. And so typically what you do for that is you'll just use the same letter that you used for the vector, but just not use a vector arrow since the coordinates themselves are not vectors. So I'm going to use the letter x for the coordinates, and I'm going to index them 1 through n, just to stay general. So I'll say x1 for the first coordinate, x2 for the second coordinate, all the way up to xn for the last coordinate. So this is a general vector, a general coordinate vector in Rn. And from now on, I'll just say vector. And almost always I mean a coordinate vector. And even if I did mean geometric vector, well, geometric vector is also a coordinate vector, so it's not wrong to just drop the distinction and just say vector all the time. So any vector x in Rn is a linear combination. So I'm already saying it's a linear combination of something without even making any assumptions about what the coordinates are. So that if that sounds like a strong claim, it is. So this vector is a linear combination of the standard basis vectors. So of E1, let's just finish the sentence too. The standard basis vectors E1, E2, all the way up to En. So how do we know that? Well, let's prove it. Let me prove it to you in general. So the proof goes like this. Well, let's just start by writing our vector x out. It has coordinates x1, x2, all the way up to xn. So that's our vector x. So what I'm going to do is I'm going to decompose this vector into a sum of several vectors. So I'm going to write this as the vector x1 and then 0, 0, and really just a 0 for every other coordinate. So really this is the vector whose first coordinate is the same as the first coordinate of x, but every other coordinate is a 0. Now, of course, this equals sign is claiming that these two things are equal with what I have currently written, and that can't be true, right? Because these are all zeros. So this is not true in the way I've currently written, so I'm going to have to write some more here. We're going to add another vector. We're going to add the second vector, which is going to have a 0, and it's going to have x2 in the second coordinate. So whatever the second coordinate of the vector x was, that's going to be the second coordinate of this second vector. But every other coordinate is going to be equal to 0. And I'll carry on in this pattern until the very last vector in this sum is going to have a 0 for every single coordinate, but its last coordinate is going to be the same as the last coordinate of x that I should point up here. So the last coordinate is going to be xn. So the idea is, first coordinate, it's got the first coordinate of x, everything else is a 0. The second vector, its second coordinate is the second coordinate of the vector x, but every other coordinate is 0. If I had written the list out in more detail and I had written out the third vector, well, its third coordinate would be equal to x3, whatever the third coordinate of the vector x is, and all other coordinates are going to be 0. And then finally, when you get to the very last vector in this sum, the last coordinate is the same as the last coordinate of x, and all other coordinates are equal to 0. That's the pattern here. And these coordinates of the vector x, like in other words, x1, x2, all the way up to xn, they aren't vectors, they're scalars. So we can treat them like scalars. In other words, we can express this sum, and each vector in this sum, a little bit differently. We can write this as x1 times the vector 1, 0, 0, all the way up to the last coordinate of 0. So really, I've just replaced this vector with the scalar product of x1 and this vector, which has a 1 in the first coordinate and zeros elsewhere. Well, does that work? Of course, because if I multiply the x1 into every single coordinate, what are you going to get? You're going to get exactly this vector here. So let's do the same thing with this next vector. I'm just going to pull this x2 out of that vector as a scalar, and I'm going to get plus x2 times 0, 1, 0, dot, 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 all the way to 0, right? So it's the vector who's got a 1 in the second position and a 0 in every other coordinate. And again, that would work, because if I took the x2, can check backwards in reverse, you take the x2 and multiply it into every single entry. And what are you going to get? You're going to get exactly this vector up here. So that works. And then do the same thing for the last one. We've got, and so on and so forth through every single vector in the list. You're going to have, with this last one, if I pull the xn out of that vector as a scalar multiple, I'm going to have xn times 0, 0, all these zeros won't change, and then I'll have now a 1 for the final coordinate. Right, but look what happened. This is E1. This is the standard basis vector E1 in Rn. And this vector here is the standard basis vector E2, because it's got a 1 in the second position and zeros everywhere else. And that would work just fine for every other vector in the list. And finally, when you get to the last one, this is going to be En, because it's the standard basis vector of Rn that has a 1 in the nth coordinate and is zeros everywhere else. So really what this is it's x1, which is a scalar, times E1 plus x2 times E2, the vector E2, and all the way up to the very last term, which is going to be xn, which is a scalar, again, times the vector En. So what that means, if you chain these equalities together, what we've done is we've written the vector x as a linear combination of the standard basis vectors, because look what we have. We have some scalar. We don't have to call it C1 like we did in the definition of linear combination, because that was just a label. As long as it's a scalar, that's perfectly fine. So we've got some number, x1, times the first vector in this list, which is E1. Then we've got some number times the second vector in the list. All the way up to the very last one, we've got some number times the final vector in this list, En. And then we're adding up all those terms together. That's exactly what it means to be a linear combination of the vectors E1, E2, all the way up to En. Right? The fact that these scalars came directly from the vector x is what allowed us to make this work and do it. But all the same, the fact remains that we've taken the vector x and we've got it as a scalar times E1 plus a scalar times E2, and plus a scalar times each of the vectors in this list all the way to the last one, a scalar times En. And because we can do that, that's what it means to say that this vector x is a linear combination of those vectors. So we don't even have to make any other comment on that. We can just draw our proof box to indicate that that's complete. So that's your second example, which is a bit more general, but that is another example of linear combination. So basically every vector is a linear combination of some other vectors, in particular the standard basis vectors. Okay, well, let's look at an example of when this could fail, because all of the examples so far have been framed in a positive way, in the sense that the definition of a linear combination has been satisfied. But what if it's not possible to do? Like in this example, the wording strongly suggests that that's going to be the case. So we've got a vector here, which is a vector in R4, because it's got 4 coordinates. It's written as a column matrix, but it's still a column vector. So show that this vector is not a linear combination of these 3 vectors that we've got over here. So, well, how would you do that? Maybe it's one thing to just not be able to show that this vector is a linear combination of these other 3 vectors here, but how are you supposed to show that it, not only that you can't do it, but that it cannot be even done? Because that's what it would mean. If to show that this vector is not a linear combination of these 3 vectors, we have to show that it's impossible to come up with scalars. A scalar to multiply onto this vector, a scalar to multiply onto this vector, and a scalar to multiply onto this vector. And we could take anything we like, but we have to show that no matter what we take, once we add those vectors together, the result will never equal this vector. That's what it would mean to show that this is not a linear combination of these vectors. So that sounds ambitious, and it might sound a bit tough in the sense of how are you supposed to begin that. But the good news is there's a standard procedure. And what's even better is that if I had changed this example to give you a completely different choice of vectors, but maybe it was an example that was worded in a more positive light, and you were asked to show that a certain vector is a linear combination of a handful of other vectors. Well, that changes the problem entirely, but the good news is the way we approach it is going to be the same. So for that reason, this is going to be a nice procedure that you can use in a wide variety of problems. So the way we're going to start here is we're just going to, because we're trying to show that this can't be done, we're going to start off by just assuming, just for argument's sake, that it could be done. Or what we're really doing is we're setting ourselves up to make a contradiction argument. So we're going to suppose, and what you're really doing is you have a contradiction in mind. But we're going to say, suppose that this can be done. Suppose that this vector is a linear combination of these other three vectors. Well, that would mean that we could do the following. We'd be able to write the vector 1, 4, 1, 3 as a linear combination of these other three vectors. Well, that means we can write, say, some scalar C1 times 1, 0, 1, 0 plus another scalar times the second vector in our list, which is 0, 1, 0, 1. And then lastly, plus a third scalar times our final vector, negative 1, 0, 0, negative 1. Okay, so that's what it would mean. Let's say, suppose that this is true for some scalars C1, C2, and C3. That's how you want to start these, right? Whether you're trying to show that a vector is equal to a linear combination, or is a linear combination of some other vectors, or maybe showing that it's not. You're going to start this off in the exact same way. But now what do? Well, now you just follow this out. Chase it down and see what happens, right? Play it forward. Play the tape forward, as some people say. So what does it mean if you can do this? Well, actually quite a bit. And you can get somewhere with this, because now what happens if we take the C1 and just multiply it into this vector? So just multiply each of those 4 entries by C1. And then for the second term, just take each of those 4 entries and multiply it by C2. And then finally take each of these 4 entries and multiply it by C3. So what that's going to give you then is a new equation, which is slightly more condensed. So 1, 4, 1, 3. So what are we going to get here? We're going to get C1, 0, C1, 0. Right, that's our first vector. Then the second one, we're going to have 0, C2, 0, and C2. Right, if I multiply the C2 into that vector, I'm going to have 0, C2, 0, and C2. And then the last one here, if I multiply C3 into this vector, I'm going to have negative C3, 0, 0, negative C3. All right, so then I could take this one step further now, and I could actually add all 3 of these vectors together. Which, how am I going to do that? I'm going to do it entry by entry, right? And I'm going to add so if I want to get collapse this into one vector, I'm really just going to add up the first coordinates of all 3 of these vectors. And then if I want to get the second coordinate of the result of the sum of all 3 of these vectors, well, I'm just going to add up the second coordinate of each individual vector. That's how we're going to do it. But let's save that for the next line. So then let's put the grammar back in this. So how does this read? Then this vector is equal to the sum of these 3 vectors, and hence we can write, hence this, we'll say 1, 4, 1, 3. This is going to be equal to what? Well, on the right-hand side, if you add up the first coordinate of each of those vectors, you're just going to get C1 plus 0 minus C3. So we're going to get C1 minus C3. Then for the second coordinate, add up the second coordinates of each of the vectors. We're going to get 0 plus C2 plus 0, so that's just going to be C2. Then for the third coordinates, C1 plus 0 plus 0, that's going to be C1. And then the last coordinate of each vector is 0 plus C2 minus C3. So we're going to have C2 minus C3. Okay? So that's what we get. And I'm going to use a phrase to refer to the steps that we just did, particularly going from here to here and then going from here to here. So this is called the following: collapsing the right-hand side. Okay, so that's what I mean. If I use that phrase, just collapse the right-hand side, it's probably because I'm referring to something that looks like this form, and I really just mean multiply all the scalars in, like we did in this step, and then add the vectors together so that they're a single vector. So we've collapsed this all down into one vector. Imagine you had a deck of cards that was spread out all over the table, and you just kind of squish them together so they're in a nice, neat pile. That's kind of what I mean by collapsing this expression. Just collapse it into a single vector. That's a phrase I'm going to use quite often. So that I want to make a point of saying that. In fact, I might even just go all the way to underline it. Okay, so now what good is this? Which that doesn't mean we're done, right? What does this have to do with being a linear combination? What does this have to do with testing whether this vector is a linear combination of these three vectors? Well, this is an equation of two vectors in R4. What does it mean for two vectors to be equal? Well, it means each of their coordinates are equal. So what this tells us is that, well, C1 minus C3, that had better equal 1. C2, it had better equal 4. And C1, it had better equal 1. And C2 minus C3, finally, that's going to have to equal 3. So this gives the system, which is a linear system, so this yields the linear system. What are we going to get? Let's write it out carefully. So the first equation of C1 minus C3 is equal to 1. That's the first equation. The second equation says that C2 is equal to 4. Third equation, says that C1 is equal to 1. And then the fourth equation says that C2 minus C3 is equal to 3. So that's a linear system. That really, this linear system must be satisfied if this statement is true, right? Saying that this is true is the same as saying that this linear system is satisfied. So let's take a look at this linear system more closely on the next page and see if it has a solution. And if it does, we'll see what the solution is. In other words, what values of C1, C3, and C2 would make this linear system be satisfied? Really, that's what it would mean to come up with values C1, C2, and C3. That little bit that I told you I hadn't shown you on the previous page, really, this is the strategy that you would use. But let's finish the example on the next page.